Hello all, welcome back to Electronic Devices and Circuits video lecture series. I am BVV Satyanarayana, Associate Professor in Department of ECE, Vishnu Institute of Technology, Bhimavaram. In unit number 3, rectifiers and filters, we already discussed about introduction to RPS, basic rectifier setup, half-wave rectifier operation and waveforms. Now in this video, we will discuss center tapped full wave rectifier circuit diagram, operation and waveforms. Center tapped full wave rectifier. The objectives of this lecture are the circuit diagram of center tapped full wave rectifier, operation of center tapped full wave rectifier, waveforms of center tapped full wave rectifier. In off wave rectifier, the current is flowing through the load during positive off cycle only, and no current is flowing through the load during negative off cycle. And hence only positive off cycles are rectified in off wave rectifier. The full wave rectifier conducts for both positive and negative off cycles of the input signal. Means in this full wave rectifier we can rectify both positive and negative off cycles. In order to rectify both positive and negative off cycles, two diodes and one center tapper transformer are required. And those two diodes must feed a common load. Here in center tapper transformer based full wave rectifier, the load is very important. The load must be arranged in such a way that the current during positive and negative off cycles must flow in the same direction. And this is the center tapper transformer used in this rectifier. Here the secondary of the transformer is tapered at the center. Because of center tapping, the number of turns in the upper portion is same as that of the number of turns in the lower portion. So two equal magnitude and opposite phases signals are developed within the center tapper transformer. If suppose during positive off cycle of the input, this terminal A is positive with respect to the terminal C. I am calling this as terminal C. So terminal A is positive with respect to terminal C, means it's a negative. Similarly, this terminal B is negative with respect to terminal C. Means this terminal C, it can act as a ground. So at terminal A we are getting positive and terminal B we are getting negative during the positive off cycle of the input. And hence a positive off cycle is developed across the upper portion, and equal magnitude and opposite phase means a negative off cycle is developed during the lower portion. Similarly, if you consider the negative off cycle of the input, during this negative off cycle of the input, this terminal A is negative with respect to terminal B, and this terminal B is positive with respect to terminal C. So again it acts as a ground. So a negative signal is developed during the upper portion and a positive signal is developed in the lower portion. So in the transformer secondary, we are getting two equal magnitude and opposite phases signals. And these two signals P drives two diodes. And these two diodes conducts in alternative off cycles, and these two diodes drives the common load. The two, we are arranging that load in such a way that the current during positive off cycle and negative off cycle is flowing in the same direction. So this is the center taper transformer. If you observe the waveforms, the input signal applied at the primary and upper portion signal both are in phase. Both are in phase. And input signal, lower portion signal, if you observe, both are having equal magnitude and opposite phase. That is the action of center taper transformer. Now this center taper transformer with two diodes we are using in this center taper full wave rectifier. This is the center taper full wave rectifier circuit diagram. This is the circuit diagram which consists of one center taper transformer and two diodes, and those two diodes drives a common load. And coming to the operation of the center tapped full wave rectifier. During positive off cycle of the input AC signal, a positive off cycle is developed in the upper portion and a negative off cycle is developed in the lower portion. And this positive off cycle is applied to diode D1, that is the anode of the D1. So this diode D1, it is in forward bias and it conducts and it can supply current to the load. And at the same time, in the lower portion, a negative off cycle is developed. That negative off cycle is applied to anode of the diode D2, and hence diode D2 is reverse biased. It is in off state. It can act as a open circuit and no current it supplies to the load. So during the positive off cycle, the load current IL equal to ID1 means only diode D1 it drives the load. Whereas diode D2 it is in off state, so it cannot supply any current to the load. So we can say the positive off cycle is developed across the load. So I am applying the positive off cycle, and this positive off cycle it is reproduced in the load. During negative off cycle of the input AC signal, if you consider suppose, then a negative off cycle is developed in the upper portion and a positive off cycle is developed in the lower portion. This negative off cycle is applied to anode of diode D1 and hence the diode D1 it is reverse biased. It is said to be in off state, so it doesn't conduct. It cannot supply any load current. Whereas in the lower portion we are getting a positive off cycle. The positive off cycle is connected to anode of the diode D2 and hence the diode D2 is forward biased. It can conduct. It supplies current to the load. So during this negative off cycle, IL is equal to ID2. Means this diode D2 it drives the load and supplies current to the load. Here the very important point is, even though the input is negative off cycle, the current flowing through the load is the direction of the current flowing through the load is same as that of the positive off cycle. So in the previous case, this is the current direction. For positive off cycle, this is the current direction. And whereas for negative off cycle, the current it is in the same direction. So here we are arranging this load RL in such a way that the current flowing through the load is always in the same direction, irrespective of the input. So ID1 and ID2 having same direction within the load. So if you calculate the total load current for one complete cycle, then IL equal to ID1 plus ID2. ID1 plus ID2. That is the total load current for a full cycle. So here one more important point is, so I am considering the negative off cycle of the input AC signal and the current direction it is same as that of the positive off cycle through the load. So this negative off cycle it is converted to the positive And hence, even though the input is negative half cycle, a positive half cycle is developed across the load. Means negative half cycle, it is converted to the positive half cycle. Previously, for positive half cycle of the input, a positive half cycle is developed across the load. Now, even though it's a negative half cycle, because of the load arrangement, that negative half cycle, it is converted to the positive half cycle. So the bidirectional input AC signal is converted to the unidirectional signal. So even in negative half cycle also, there is a current flowing through the load. And coming to the waveforms of center tapped full wave rectifier, these are the waveforms. So the first waveform, it is the input signal, input AC signal. And the second waveform, it is ID1 during positive half cycle. And the next waveform, it is ID2. And next waveform is IL, which is equal to ID1 plus ID2, that is the total load current. And the last waveform, it is the load voltage. So I already told the input signal, it's a AC signal. So it's a sinusoidal signal. That too, it's a bidirectional signal. It's a bidirectional signal. So let me take a different color. Yeah, this is the bidirectional input signal. Okay, positive half cycle and the negative half cycle. Again, positive half cycle and the negative half cycle. That is applied to the transformer primary. Okay, for this input signal, two signals are developed across the secondary. One in the upper portion and two other one it is in the lower portion. Both are having equal magnitude and opposite phases. If you want, you can draw those two waveforms also. So here, for our convenience, I am skipping those two waveforms. So directly I am considering the input signal. So during the positive half cycle of the input signal, diode D1 is forward biased and it conducts, so supplies current to the load. So the positive half cycle, we are getting ID1, there is a ID1. At the same time, during this positive half cycle, diode D2 is reverse biased and hence it doesn't conduct. So ID2 is equal to 0. And during negative half cycle of the input, diode D1 is reverse biased, it doesn't conduct. So current is 0. And during the same negative half cycle, diode D2, it is forward biased. It conducts and can supply current to the load. So we are getting a positive half cycle. Okay. So likewise, we are getting D1 conducts during positive half cycle and D2 conducts during the negative half cycle. So these are the ID1 and ID2 currents. Now, if you want the total load current, then add these two waveforms, ID1 and ID2. If you add, then we are getting all positive half cycles. This is positive half cycle and again positive half cycle. So likewise, we are getting only positive half cycles. And load voltage, it is proportional to load current. I already told VL equal to IL into RL. RL is constant, so both are proportional. So again, load voltage is also it's positive half cycles. So these are the waveforms. If you want, you can draw the voltage across the diode also. So where in the previous case, half wave rectifier case, during negative half cycle, maximum voltage is dropped across the diode, that is VM. Whereas here in the secondary, there are two VMs. And the VM plus VM 2VM, the total 2VM, it is dropped across the reverse biased diode. So if you observe the circuit diagram clearly, uh, if you observe the operation of this center tapped full wave rectifier clearly, at any time only one diode it is in forward bias, the other diode is in the reverse bias. So voltage drop across the reverse bias diode is 2 Vm. Across the secondary, we are getting Vm in the upper portion and Vm in the lower portion. That Vm plus Vm 2 Vm, it is developed across the um, reverse biased diode. So the peak inverse voltage of this center tapped full wave rectifier is 2 Vm. And here the input, it's a bidirectional signal, AC signal, whereas and the output, it's a unidirectional. It consists of only positive off cycles. Okay, still there is more AC component in the output. That's why this we can call it as a pulsating DC. Pulsating DC. The output is not perfect DC. It is pulsating nature, pulsating DC. And coming to the summary, in this lecture we have learned the following: the circuit diagram of center tapped full wave rectifier, operation of center tapped full wave rectifier during positive off cycle and negative off cycle, and the waveforms of center tapped full wave rectifier. In the next lecture, I am trying to give some brief details about bridge rectifier. Thank you. Thank you all.